And the first example that we're going to look at here is birefringence. So we very simply have a linearly polarized Gaussian wave, which is going to propagate through a uniaxial crystal, a calcite crystal. And we're going to orientate the optic axis of this crystal with respect to the direction of propagation of the beam and its polarization, so that the birefringence effect inside the uniaxial crystal will separate two different polarization states inside the crystal. And so we'll get two replicas or two modes, two beams out of that initial single beam after it has propagated inside the crystal. So let's go directly to VirtualLab Fusion for this example. Here we are again. The system, as we can see, is rather straightforward from the point of view of the number of components that we have. We have our Gaussian wave source, we have our calcite block, and we have a detector to observe the field, the light, after it leaves this crystal block. So initially, our light is polarized along X. It's linearly polarized along the X-axis of the global reference, the global coordinate system of the setup. Now, this is, of course, we have a lot of possible references here. The crystal itself is going to provide, it's going to impose a given coordinate system on the problem. So we start from this polarization state that we define in the source refers to the coordinate system of the source itself. Then let's take a look at our calcite block. So we are using a crystal plate component. This is one of the new features and which implements the new technology, the new solver for anisotropic media. We have the possibility of using that new solver inside the crystal plate component or as a layer in coatings. Also, we're going to see an example about that later on, but in a coating it can be in combination with isotropic media as well. So it can be one layer of many, that anisotropic medium. But here we have simply a crystal plate component, and we can define the medium that we're using in this type of calcite crystal, and we can of course define the orientation. And this is what this is also referred to that global coordinate system provided by the source. So we set here the theta and phi angles of the crystal of this anisotropic medium. We can observe, we can see graphically represented the qualities of this anisotropic medium by clicking here on this view button, and we're going to see the ellipsoid, the index ellipsoid corresponding to this crystal, and this gives you different, you can enter a given direction here that will help you visualize how things are set in the problem, in the system itself. So this new feature, this new solver for crystals and anisotropic media comes also with this added visualization tool specific to such media or media with such properties. So we have set it up in this way, so that the beam impinges at an angle with respect to the optic axis, and we can generate that birefringence effect. Note this phi at 45 degrees. Remember that the initial polarization was linearly polarized at 0 degrees. And so we click OK here. And then finally we have a detector that is going to allow us to visualize a field as well as a polarization state, the polarization ellipses at this plane. And you can see the small angle icon here in the positioning controls of this detector. If I go to orientation parameters, we can see this rotation angle around Z, also of 45 degrees. This means that we are going to rotate the detector in its plane, so we're not going to change the detector plane, but we're going to rotate around that main propagation direction that is Z in order to place or to locate the two replicas of the beam, the two beams that will be generated by or split by that birefringence effect along the horizontal of our detector. We can take a look later at what happens if we do not use this 45-degree control here in the detector. And so, without any more talk, I'm just going to run the simulation of the system with field tracing, and we can see here the two replicas, or the two sub-beams, the two modes into which our original beam has been split by that birefringence effect of a calcite crystal. If I zoom in, we can observe the polarization state of each of these replicas, each of these modes, one along the horizontal axis, one along the vertical. Note that we have rotated the detector 45 degrees, and that will influence the definition of a polarization at this plane exclusively. Let me illustrate that by simply removing here this 45-degree angle and setting it to 0. That means we, of course, do not use that rotation, and run the simulation again. We're still going to get the same physical result, but now at 45 degrees. And again, the inclination of those polarization ellipses, which in this case are lines at orthogonal polarization states, linearly polarized, are also have a different inclination because of that rotation of the detector. So this lets us see or visualize what the effect of that rotation in the detector plane is. Evidently, we're changing the coordinate system of that detector exclusively. And we could, of course, perform parameter variations here in this system, the thickness of the crystal, and we can see all those results in the example. Let me open the files, the corresponding files, although we also have the results on the slides. So here we have a parameter run. This allows us to vary parameters in the system and observe their effect on the different detectors which have been included. And what we change here, we could select any system parameter to change, but what we are actually doing here is change the thickness of our calcite block. And the simulations have been run already. Let's advance, let's move on, and we can create an animation out of this sequence of results. We can see here in the top row the values of the thickness of our calcite block and the corresponding results. Again, the simulations have already been run in advance. If I double click here, this will create the corresponding animation of this result, and we can see how the separation of the two outgoing beams changes as the thickness of the crystal increases, and we can see that effect in video form, in an animated form. Another interesting effect which we can investigate with this new anisotropic solver and VirtualLab fusion is the following polarization conversion in uniaxial crystals. When anisotropic media are introduced in optics education generally, one of the first notions that one encounters is that if we're talking about a collimated beam, about a plane wave, and that plane wave propagates parallel to the optic axis of the crystal, which means that its polarization state is going to lie in one way or another in the normal plane to that optic axis, then because all those polarization states are equivalent with respect to the reference provided by the crystal, then no tangible effect will appear. However, that assumes that we're working with a plane wave and that we can consider that the polarization vector, that the field is going to vibrate in one way or another, but that we can assume it's going to be contained in that normal plane to the optic axis. In this experiment that we're going to perform for this example, that we have performed for this example, we focus light onto the crystal. And it is true that the main propagation direction is along the optic axis, but because we no longer have an ideal plane wave or a beam which can in any way be assumed to be collimated, and therefore that focusing effect is going to cause that assumption that the polarization vector, the field vector, is going to lie in the normal plane to the optic axis. That is no longer true. It can no longer be true. And because of this, interesting effects will appear in this experiment. Once again, we use a scientific publication as a reference. Experimental measurements from that publication on the left of this slide. On the right, we have the results generated with VirtualLab Fusion. So this solver works for collimated beams for ideal plane waves, but also, as it's demonstrated here, it works just as well because of the general framework that is used and the very comprehensive framework that is used. It works just as well for focused light as in this example, and we can observe how the interesting effects that appear, those vortex, those phase dislocations that are caused by the propagation through the crystal, are also reflected in the simulation result of this example. This example showcases the use of anisotropic media as one layer among many, alongside isotropic media as well, in a coating. This means we can, in VirtualLab Fusion, make any combination of isotropic and anisotropic layers in a coating, and that is the feature that is used in this example. Again, we take a scientific publication as a reference for this simulation experiment. The background here, the technical application background, is an LCD display, and the additional polarization handling and play that we can perform with the inclusion of anisotropic media in this stack, in this layer stack, means we can, or the authors of the initial paper demonstrated, that it is possible with that strategy to recycle more backlight for an LCD in the construction of an LCD. And that is as I said, the background, the technical background, the application background of this experiment. And in that publication, as we do in this use case with the use of VirtualLab Fusion, they investigate the different parameters that go into the functionality of the device. And just as one example here, one of the results that are demonstrated or investigated in that initial paper and that we replicate with simulations and VirtualLab Fusion is how the number of layers will influence the efficiency of the device across, in this case, the abscissa represents the wavelength of the radiation, and of course we want to cover as broad a range as possible. Later on, the premise of the paper, of the initial paper, goes they combine not just one multi-layer setup as is investigated here, but they combine several with different thicknesses and different configurations in order to cover a broader spectrum. So there are additional conclusions and additional studies in that initial publication, and it is clearly visible here how with 20 layers the Bragg reflection condition is not fulfilled yet. We reach we don't even reach 80% efficiency. And then we can see in addition the results for 50 layers and 100 layers, and according to the conclusions of a paper, taking into consideration also fabrication constraints. In this case, for the purposes of that paper, the 50 layer situation would be enough here. And just let's close this with a brief look into VirtualLab Fusion, how those layers, isotropic and anisotropic, can be combined in a single coating, as we discussed. Here we are again. We have a very simple setup, very straightforward setup with a plane wave source, a stratified media component, and an efficiency detector. And in this stratified media component is where we have that multi-layer stack. In this case, this is just for one stack, and then, as I said, additional stacks are combined to increase the wavelength range in which the device is going to function. So that would be, as I said, an additional premise or an additional conclusion of the paper. But let's just, from the point of view of being interested in the new features of VirtualLab Fusion 2021.1, let's take a look at that coating, how that coating is defined, and in that combination of isotropic and anisotropic media. And that's what we have right now on screen. We start with a uniaxial crystal layer. We can manipulate the orientation, of course, that is fundamental when we talk about anisotropy. And then the next layer would be isotropic, then the orientation does not matter. So we cannot enter that parameter, we cannot manipulate that parameter. Then crystal again, isotropic again, and so on and so forth. And this takes us to the last block of content for the day, microlens arrays.